Here's a short section of little videos all about magnetism, and we'll talk them through as we go along. So to start with, we have something that will detect magnetism, which is a magnet. I've got a free-flowing magnet here. You can see it being affected by something out of sight. So my magnet in the foreground, even though it's a good 15-20 centimeters away, will affect it. A couple of quick things. Magnets don't all look like that. Okay, with or without the string, they don't all look like bars. So the one I'm moving here, for example, as I rotate it, you can see it rotates the other compass. So it gets quite, the magnet in the compass, it gets a little bit complicated when we start looking into detail. But this also looks like a bar, except my poles are actually in the side. Yeah, so the poles of this one are in the end. Okay, so they can be different places, and they will either obviously attract, or they will not attract, they will repel. Now, just to give a quick heads up, that will attract, but I can't make this repel. Okay, so this is just a piece of ferrous metal, something that will attract a magnetic field. This is the magnet. So I can't tell if this is just a bar of metal or if it's a magnet until I either bring it near something like a compass, which is really another magnet, or I get the effect where I can start pushing things around. Okay, so ultimately the best way of testing magnetism is to get two magnets, and the way to think all of our topic is think about it in terms of what magnets can do. So if you put two together and you put them repelling, then that's the most useful concept, because we can just simply get them to change how they behave. So if I lift that off, I can get repulsion. So all of our magnetic machines are about repelling. Here I've got a soft iron piece of wire. At the moment it's not magnetic, because although I've been playing with it, it doesn't keep its magnetism. But if I get a magnet, and these are really strong, you can see their effect on the compass over there. If I put this on, then I'm inducing magnetism into it, and you can see it's a pretty strong magnet. It's picking up a lot of big paper clips. But as soon as I remove that, yeah, it decays away really rapidly. So all the domains in here will readjust. Okay, so I've lined them all up, but if I let this go, then it drops them. As soon as the domains are overall facing another way, or enough of them are facing in different directions to not be magnetic enough to pick up the clips drop off. So this is no longer magnetic. Okay, it is soft material, it's a soft iron. Okay, recreation of Oersted experiment. If you just put a wire on top of the compass and we turn on the current, straight away you can see an effect. That's about 0.5 amp, and as we turn it up, you'll see a bigger effect. Now if we turn that off and put the wire at 90 degrees, well, field wraps around it, so I'll turn it back on. If we turn that right up, we can actually get enough to flip the compass. So the current flows in the right direction to turn the coil so that our north side is on this way. We're getting a massive current flowing from right to left in the picture. Okay, if I turn it down from 3.8 amps, that's a lot of amps, turn it down, then you get to a point at which the Earth's magnetic field is stronger. There we go. So it's not a strong magnetic effect, sensitive enough compass, it will work. Okay, next step up from Oersted's experiments. We've got a solenoid now. I've obviously homemade around a test tube. No voltage at the moment, but if I start to turn up the voltage, then you can start to see the effect on the compass. Okay, and it will drag it around, but it'll only drag it around so far. And at the moment we've got, just turn that down a bit because it's a bit much, 2.5 amps flowing through this wire. So it's fairly big. But the effect on it is not actually getting it to line up with a magnetic field. Now, if I stick a ferromagnetic core in the middle, then you can see a much larger effect. Okay, so it instantly turns. So it's a way of amplifying it. The nail in here has a much bigger effect than the coil on its own. The coil is inducing magnetism into the nail. Okay, here we have a simple electromagnet. It's got 1100 turns. Just turn it over, you can see it a bit more carefully. What I've got here is a detector, i.e. a compass. Now our field lines will be coming out through the pole, so again just remember our direction, either that way or that way, directing away from the compass, but either way it will start to come out and it'll spread around. So roughly 90 degrees to what we've got at the moment. Okay, now if I turn up, just to give you an idea of scale materials, I'm starting to get a measurable effect. You're starting to see some turning going on over here on my compass. Okay, but I've actually got to get up to reasonably high, you know, almost 2 amps flowing through here to make that work. Okay, so the other way of doing it, again, if I just turn it off, okay, that will reset itself, my compass down here, but if I just put it there, it'll be a bit more obvious. Okay, so a little bit of effect there, but if I take again, ferromagnetic material and I stick it in, notice how much definite movement we get from that. Okay, so that is just putting that inside makes that a much stronger field. And here we have a coil, so again quite narrow, it's only 300 turns, not huge, but if I put my compass in so you can see it and I turn it on, you can see the magnetic field is really strong. So just the fact that I made it into a narrow coil is so much stronger than a single wire on its own. There we go, as it recovers. So nothing to stay magnetic, no material in the middle,